Hello, in this video I want to talk about the seemingly strange behavior of charges in combined electric and magnetic fields. So we have a setup in which we will have very simple magnetic and electric fields which will be static, which means they don't vary in time, of fixed magnitude everywhere in space, uniform in space. And we know that the force exerted on such a particle with a charge q is given by the cross product between the velocity of the charge and the magnetic field plus the electric field. So that's the well-known Lorentz force. So we will look first at simpler cases. And the simplest case, of course, is with the electric field in a single direction. Like, for example, the electric field is E0, 0, so along the x-axis, and no component on the y and z axis. And let's suppose we have a particle that's initially at rest. Then we know that F equals m t2 x. Second derivative with respect to time equals, well, q times e, which means that the movement of this particle will be a movement in the x direction. So we have the electric field this way, and our charge q will accelerate this way with the uniform acceleration. Now on the next board, we will look at a bit more complex movement in a uniform magnetic field. And this is something also that's well known, that's covered in many basic electromagnetic courses. But we'll just review it because it will be helpful for us in the combined fields, in which we will be able to determine the motion of the charge without having to solve complex differential equations, which is always nice to do. Now we go to the second case, in which we have a uniform magnetic field pointing in the z direction, and we will look at the motion of a particle in the xy plane. So let's suppose that we have our reference frame here, the y direction is here, the x direction is here, and the z direction is pointing out of the blackboard, and this is often represented by a circle and a dot in the middle. And we have a particle q of a charge q and mass m. So we could write differential equation for the motions and solve them, and what we will do in this case will be the force. So m dv dt equals to q times v cross b, and we can write v as vx, vy, and vz, and we will have a couple differential equations, and we can solve that. That's not what we're going to do, but keep in mind that the equation looks like this because it will be useful on the next board. What we'll do is we're going to think about it. It's always fun in physics when you can just avoid a lot of math and instead think about the problem and find the solution. So what's happening here? We have a particle which is moving at a certain velocity v in the xy plane, and there's a force on it exerted by the magnetic field. So what is the force? Well, the force is first of magnitude q times the magnitude of the vector, the velocity vector, times the magnitude of the magnetic field. Here we know that this magnitude b is simply the value b here of the that we gave in the z direction, and the direction of the force will be perpendicular to the speed, to the velocity, and the magnetic field. So we use the right-hand rule. Like, there are many versions. Me, I like the palm version, in which you have your first vector in this direction, the second vector in this direction, the third direction is like you just hit it, just move this way. I think it's clearer than the one with 3 fingers, and it's easier to achieve. So A cross B equals C in this direction of the palm. So what we do is we have the magnetic field here, this velocity vector here. So velocity, magnetic field, and there will be a force in this direction for a charge Q, a positive charge Q, and the force will be in this direction. Of course, if Q is negative, the force will be in the other direction. So what we see is that the force is perpendicular to the velocity vector. So the magnitude of the velocity, so the speed of the particle, will not change in time because there's no force in the direction in which the particle is moving. And what this will do, this will deflect the particle. Now, we have two ways of seeing what the motion will be. The first one is, we've seen in mechanics that when there's a force perpendicular to the motion of the particle, because the velocity is tangent to the trajectory of the particle, and the force is constant, we know that the movement is a circle traversed at a uniform speed. So that's basically the case in which we have a rock at the end of a rope. There's a constant, at constant speed, there's a constant force, and we obtain a circle. The other way of saying that is that, well, as to the velocity is concerned, the magnetic field is the same whatever the direction you're going. The magnetic field is always in the z direction, and whether you're going this way, this way, or this way, or this way, there's no difference. The force will have the same effect. And the only way by symmetry to have always the same effect of this force in this plane is if we get a circle, because we start with a certain velocity, then we will change direction. We change direction a bit, and we change direction by the same amount each time. And what this gives is going to be a circle. So we know that the movement of this particle will be a circle, so the movement will be circle. Now, if we have a circle, we know that the force here is equal to the centripetal acceleration times the mass. So we can use these equations to get two informations. The first one will be the radius of the circle, and the second one will be the angular velocity, the angular speed along the circle. So, first one we will see if we put m v square over r, there will be a radius r and angular speed omega. We know that mv squared over r equals to q vb, and we can usually, what we do is we combine the m, q and v together, q and b together. We say that, and we can simplify this to v over r equals to m q b over m. And we know that this here is equal to the angular speed omega, and we call it omega c because the movement of these particles in a magnetic field is called the cyclotron movement. So here we have the omega c equals a qb over m, and we can plug this back into this and get, if we want, the radius of the circle, which I won't do here. You can do that as homework if you want. So that's the two movements that we have. Now, if you think about it, we like to solve problems without solving equations. That's what I said a few minutes ago. So let's say, okay, if this particle here is in a magnetic field, it's rotating this way. It's turning in the plane. And if the particle is a pure electric field, it's going parallel to the electric field. So we would think that if we combine these two, well, we combine a movement in this direction and a circle, we will get a movement that looks like this. And unfortunately, we'll see that this is wrong. This is not the movement that we get. That's the surprise here in my title. It's unexpected that we don't get this movement, and we'll do that on the next board. Okay, now we're in a situation in which we have the same particle of mass m, charge q, in a uniform magnetic and electric field combined. So both fields are present. And we have that from the Lorentz force equation that m dv dt equals to q v cross b plus e. So we will make the substitution here because we could solve this. If you want to, you can try it. If you've seen how to solve differential equations, you can solve for v and then you can solve for x. If you want to, you will get a solution that will be exactly what we will see using other solutions. That's a nice exercise if you want to try it. But as I said, in physics, we often want to solve the problem with doing the least amount of math possible. And that's what we're going to do here. And we're going to do that by introducing v prime equals to, let me see, v b e cross b, okay, e minus e cross b over b squared. So what we'll do, actually, we're changing reference frame. Let's walk our way through that. If you have two reference frames that move relative to each other, and we have a first reference frame here with x and y, and the second reference frame, I will offset them, but ideally they would be the same x, just so that we see what's happening. I will offset them a little, x prime and prime, and this one moves as a certain velocity u relative to the first one. To convert the various vectors that are used to describe our movements from one reference frame to the other, you know that we have the coordinate in x prime is equal to the coordinate in x minus u times t. Let's walk our way through that. The coordinate here in this reference frame, x prime, is here. And the coordinate in x is here. So what we want is to know what is the relationship between these two. Well, the relationship between these two is that x is equal to the distance here plus the distance here. So that's the first distance, d1. That's the second distance, d2. So x is equal to d1, which is x prime, plus the distance that's been traveled. And let's suppose that initially these two coordinate systems were at the same location, the same origin, plus u times t. And of course, if we want to know x prime, we just switch it to the other side of the equation. Now that gives us that x dot prime equals x dot minus u. So when we change reference frame, what we do is we to obtain the velocity vectors in the other different reference frame, we subtract the relative velocity between the two reference frames. So that's what we did here. We did v prime equals to v minus some constant, and we're basically switching reference frame. Now, why do we do that? We'll see that it's because the problem becomes easier to solve in the new reference frame, and then we can come back to our original reference frame to see what's happening. So that's what we'll do. Okay, now we will do the substitution, substitute v in there, and get our equation in terms of v prime. So the first term, we have dv dt, but this is a constant, we have to remember, because e and b are constant vectors, constant value of b. So when we derive with respect to time, this term disappears. So on the left-hand side, what we get is m dv prime dt, and now is equal to qe. That doesn't change because the velocity is not involved in the force due to the electric field. Now v is equal to v prime plus this quantity, so plus v prime plus e cross b over b squared all cross b. So we see that when we distribute the sum here, we will get our term in v prime cross b, which looks a lot like this, and that's useful because if we can get rid of this thing and this thing, we would come back to something we know how to solve, the movement in a uniform magnetic field. And that's why we choose this seemingly weird change of variable. It's because we will get rid of the QE term here, and we will get back to a movement in a uniform magnetic field. So if we do that, we will get QE plus v prime cross b plus, now it's going to be a term with e cross b cross b over b squared. Oh, and there's a Q missing here, sorry. There's a Q, so there's a Q here, and there's a Q here. Okay. Now, we can see that there's a chance we can do something with this term, because what is the magnitude of these things? The electric and magnetic fields are perpendicular to each other. So the magnitude of these things will be equal to E times b over b squared, and we will get E as the magnitude. The other thing now we have to see is what is the direction of this vector. So I will just draw the reference frame so that we can x, y, z, x, y, z. So the electric field is in the x direction. The magnetic field is in the z direction. So x, z, downwards. Let's see. That's my thumb. That's the rest of my hand. It's going to be downwards. So that's E cross B is pointing in the minus y direction. Now let's call this one C, whatever letter that's not often used, x, vector x. So that we'll call this one x. So now we do the cross product of a vector x with the vector b, the magnetic field. So x is down, magnetic field is in the z direction. So down, z direction, the cross product will be in this direction. And we see that the cross product is in the minus x direction. Maybe x wasn't the best choice here. Maybe I could call it the xc. Let's call it xc so that we don't mess things up. This here, so let's walk our way through that again. This xc vector is in the minus y direction. The z here is in the this way, and so the resulting vector will be this way. So it's the minus x direction, and we know that E is in the plus x direction. So actually what we get is that this term here is equal to minus QE. And it cancels out the first term in the equation. And we're left with the exact same equation we had on the previous board for a charge in a uniform magnetic field. We solved this equation in the previous boards. We know that the movement of this thing here is a circle of uniform of constant radius traversed at uniform angular velocity. So in a reference frame that follows this change, a variable that goes at this velocity relative to our lab or initial reference frame, the board frame, the one in which we want to see what the motion is, the movement is a circle. So what happens is that we have a circle, it's moving in a circle, and at the same time, the circle is moving. So how is the circle moving? We've seen that E cross B over B squared is moving in the minus y direction. So this is the equivalent of having minus E cross B over B squared moving in the plus direction. And that means that the movement of our particle will be like this. So surprisingly, adding the electric and magnetic fields doesn't result in something that is spiraling, if you want, horizontally as we would have expected, but instead as something that's moving vertically. And that's the unexpected behavior I was talking about. Okay. And all this is related to something we call the Hall effect, in which if you have a conductor, a very thin strip of conductor, and you try to pass a current through that conductor in a magnetic field, there will be a potential difference between the two sides here. And what happens is that if it, obviously in a conductor, the charges cannot just go up to infinity. They start going like this, and at some point there will be some charges accumulated here and some charges accumulated here, so positive and negative charges. They will accumulate, and at some point they will cancel this drift, if you want, and there will be a possibility for the current to go through, and this accumulation of charges here and here is what creates the Hall effect. And if we want, we can also think about what happened here in terms of the physics. So what I'll do is I will just erase the board and try to explain why we get this shape without solving any of the equations, and this will teach us why our initial intuition of maybe having the particles go this way was wrong. Let's suppose we have the particle that's going this way initially at a certain speed. So what happens is that the particle now will change direction due to the magnetic field, but it will start to slow down a bit because the electric field is now pulling this way. And as the particle keeps on doing its circular motion, it will go slower and slower and slower, so that after a while, the particle is going here, but it's going much slower than it was going here. So it will keep on moving around, changing its direction, but here, the radius of this thing, the radius of curvature here, is much smaller than here. And then it will go up here, accelerate, accelerate, and the movement will keep on going. Of course, here we have two competing effects. The first one is that the force depends on the speed, and that the displacement depends on the speed. So that's why we had to solve the equation and see exactly what's happening. But the reason why we don't get this movement is because there's a changing speed. Not only the direction of the velocity vector changes, but its magnitude. And this affects the force that's exerted on it, so that the particle will change the shape of its movement in our reference frame, because the force that's exerted on this particle depends on its speed. And that's it for today.